Okay, good. Okay, let's review quickly in case you forgot. So we started a new unit about work and energy and conservation of energy. So first of all, remember you have kinetic energy, which is energy of motion. So it's 0.5, which is 1/2 the mass, okay, the mass times the speed square. So typical conceptual question, if you multiply the speed by 3, kinetic energy is multiplied by 9 because it goes as the square of the speed. If you multiply the speed by 2, kinetic energy is multiplied by 4, but it's proportional to the mass. So the mass is inertia is in kilogram, the speed is meter per second, and here you have joule. So that will be for kinetic energy. And then you have the change. Sometimes we're going to use the change in kinetic energy. Okay, so that will be with a delta. So the change in kinetic energy will be the final kinetic energy minus the initial potential energy, and that's going to be 0.5, the mass, open the parenthesis, the speed square, so the final speed square, minus the initial speed square. So typical mistake, students will just subtract final minus initial and then square. Don't do that, okay? It's the final square minus initial square. So that will be for the change in kinetic energy. And then we have potential energy. So you have gravitational potential energy, elastic potential energy, chemical potential energy, nuclear potential energy. So the gravitational potential energy depends on the height and on the mass. So it's going to be the mass times G times delta H. So potential energy, gravitational potential energy depends on the mass and on the height. And the height is always, hello, girls. Potential energy is always depending on the height, and the height depends on the reference level. Right? So it depends where you decide that your potential energy is going to be 0. So this is the ground, and this is the mass, and that will be your delta H. Okay, so now your potential energy will be just mg delta H. So it's very simple. You are storing potential energy. If you let go, it's going to turn into kinetic energy, and then kinetic energy, it will apply a force in the desk. Okay, so we did that. And then I told you I introduced a new physical quantity. And this is in joule. This is also in joule, right? Because it's all that is in joule because it's energy. And work is a new physical quantity. And you can think of work as energy in transfer from one system to another system. Okay, so work is energy in transfer, and we're going to see that to transfer work, you need to apply a force over a distance. Okay, and the force has to be parallel to the distance. So I'm going to explain how, but let's take an example here. Let's say you are pushing something like a cart. You have all your marine biology device here to do scuba diving there. So you're pushing, and let's say there is no friction. So let's say your force is parallel. So you're pushing in this direction. So this is the force applied. Okay, so what's going to happen? The cart, it's going to increase. The speed of the cart is going to increase, right? So it's going to move faster. So there is an acceleration, F equals ma. Bless you. So it has an initial velocity, and here it's going to have a final velocity. Because you apply a force here over a distance, so that distance here, I'm going to call that delta x, okay? Then you are transferring energy from you to the cart. That energy is going to go into changing the kinetic energy, increasing kinetic energy. So you are burning fuel, you are using ATP, right? And you are transferring that energy from you to the cart. So the simple equation, okay, so the work done by you on the cart will be equals to the force applied times the distance. So it's a distance, right? It's not, you don't have to go along a straight line. Here I just simplify. I go along a straight line, but it doesn't have to be the case. If it's something like a zigzag, you have to find the total distance and you need to find the component of the force here parallel to the displacement. So you increase the energy level of the cars because you are transferring energy, and that energy will be an increase in kinetic energy. So we're going to see this is called the work energy theorem. Okay, it's like F equals ma, you are accelerating because you're applying a force. If there is an acceleration, there is a change in speed, so there is a change in kinetic energy. So it's a different way to write it. Okay, so I don't know if you remember in kinematics. In kinematics, we had this fourth equation that is very useful. Final velocity square equals initial square plus 2 times acceleration times delta x, right? We had this equation. And F equals ma, so you can hide this equation here, plus 2 times the force applied divided by the mass, delta x. And if you play with this, you will get the same thing. So that equation here comes from that theorem. You apply a force over a distance, the speed will change, the kinetic energy will change. But that force has to be parallel to the displacement. Okay, so this is just an introduction. Let's do this one here. It's easier to take some examples. Okay, so he's applying a force of 100 newtons. So this is the applied force over a distance 10 meters. So he's transferring energy from him to the crate. Okay, the crate is going to move faster. Its kinetic energy will increase. What's going to be the work done? 1000 joules. 1000 joules, very good. Okay, so he's transferring work to the crate. Okay, so we're going to say that the work done by the guy to the crate will be just force, which is 100, times the distance, which is 10. So it will be 1000 joules. Okay, so it's burning calories, transferring that energy, and the crate is going to move faster. Now, friction here is kinetic friction. So kinetic friction is doing the opposite. Okay, it's like taking money out of an account, right? You put money from the job that you have, and friction is taking away. So it's taking away energy, stealing energy, trying to make the crate go slower, trying to slow down the crate. So we say that the kinetic friction is doing negative work. So friction, the work done by friction on the crate is negative because it's taking away some of the kinetic energy, turn that into heat, maybe some noise, maybe, damaging the ground. So what's going to be the work done? Multiply the force by the distance is going to be So the force is 50 times the distance is 10, so it's going to be negative 500 joules, right? So it's like balancing an account. Money comes in, but then you withdraw money. So the net work, okay, so the net work done on the crate will be, so what comes in 1,000, but then you lose 500. So at the end you gain, or the crate gain, 5, what goes away? Go away. Don't like you. Okay, 500 joules. Okay, so that will be the total amount of energy gained by the crate. Okay, so that will be called the net work. That net work done on the crate will increase its kinetic energy. So we're going to say that the net work done on the crate, bless you, equals the change in kinetic energy. So it's going to move faster. Okay, so this is called the work energy theorem. If you want something to go faster or slower, you need to apply a force over a distance, and that force has to be parallel. If it's perpendicular, it doesn't do anything. It has to be parallel to the displacement, to the trajectory. Okay, so for example, if I have a suitcase here, right? I have a suitcase in my hand, but I move at a constant speed. Oh, that's your 3 times is to your lobe, we say in France, right? At les amours. Okay, so if I move at a constant speed, right, the force that I'm applying is up. Do you agree? Is it doing any work on the bike? Is it making it go faster or slower? No, because the force is perpendicular to the displacement, and I'm not increasing the speed, so it's doing no work. For work to be done, the force has to be parallel to the distance, right? So if I do this, yes, right, I'm pulling it forward. So in that case, you see the drawing, the force here is perpendicular to the displacement. So the guy, or I don't know what it is, the dummy here, is moving forward, but the force is perpendicular to the displacement. There is no work done because the force does not help going faster or slower. Okay? Of course, you are getting tired, but you are not doing work on the suitcase. You are doing work on the environment, right? You get sweaty and you're hot, and so all those molecules around you are going to move faster, but not the suitcase. So you are doing work on the environment, but you are not doing work on the suitcase. Likewise, there is the weight pulling down. The weight is not doing work on the suitcase. So typical question for the MCAT, for example, they love to trick you. They will say, okay, this force you are pulling up, but you are moving at a constant speed. Are you doing work on the suitcase? No, because the force is perpendicular to the displacement. The force does not help going faster or slower. It does not do any work. You have to pull to make it go faster. Okay, so for example, let's try to do this one. So the situation here, it can be confusing, but at the end, it's not that hard. You have a crate on a truck. You forget about the truck and the crate. You isolate the crate. So you focus on the crate. So the crate is in your bag. And you look at the crate. So the crate is acted upon by a static friction. So static friction, so it doesn't slide. like those crazy people who have sofa, in their truck, and it's not very well tight, and they go and the sofa left behind, okay, because you don't have enough static friction and they go too fast. So you want to make sure you have enough static friction here. That static friction, it's what is going to provide the acceleration if the truck is accelerating. Okay, so if we focus on that truck here, right, that will be your bag. It's acted upon by the weight, by the normal force. You push, it's going to push back, and static friction. Static friction is what is making the crate accelerate. Okay, it's the force, so it doesn't slide. So anyway, you focus on this free body diagram, and that's all. You need to find the work done, the net work done on the crate. And that comes from your book, so that I always say it's good if you have the same book that I'm using, which is Johnson and Cutnell. It's good for the MCAT. You can have an old publication. They are very cheap, and they have great solve problem. Very simple, but very insightful. They're very good at conceptual questions, right? Johnson and Cutnell. You do the solve problem. Yeah. Okay. So anyway, so the acceleration here is 1.5 meter per second square. You have the mass. Okay. So the only force that will be providing the acceleration, remember that the net force equals ma. So if there is an acceleration, there is a net force. The only force in this direction will be that static friction here. There is no other forces because this one is not providing the acceleration. These two are balancing each other. Normal force equals weight. Agree? Now that's from the previous unit. So we just write the net force, which is the static friction here, equals the mass, which is 120 times 1.5. Which is 180. Do you agree? Okay, so the work done by that force on the crate, it just equals 2 force times displacement. So it's just 180 times 65. Do you agree? It's just force times displacement. Okay, so that will be 12,000 joules. So that will go to the change in kinetic energy. Okay, is there any work done by the normal force on the crate? Is that force helping making the crate? No, right? So it's going to be 0. The work done by the weight on the crate is 0 too, because it's perpendicular and it doesn't help make it, it doesn't push it forward or it doesn't slow it down. So the net work is just 12 kilojoule. Or this is also equals to the net force times the distance. Okay, a different way to do it, you can say that the net work is a sum of all individual work, or you can say it's a net force times the distance. Any question? Okay. So here they make it a little bit complicated, but the work done by the weight equals 0. And then the work done by the friction. So this is the static friction. That will be the force applied, unbalanced. So the work done is force times displacement, which is and they use scientific notation, which is 1.2 times 10 to the 4 joule. This is the amount by which the energy of motion will increase. Okay? But now let's remember that a force is a vector, so it has components in 2D. So for example, 50 Newton, you are pulling with 50 Newton. It has two components. Remember, we make a parallelogram. We go from the tail to the head. Okay, we go sideways, that will be the X component. We go up and down, that will be the Y component. So the X component is how much of the force is along the displacement. And the Y component is pulling up. So the Y component is teaming up with the normal force to balance out the weight. Okay, so because if you pull up, it doesn't push as hard on the ground, so the normal force will be less. So if you want to know what's going to be the work done by you on the block, which number will you use? Which one is helping making it go faster? Is the component 40 helping making it go faster or accelerate? No. So we only use the component parallel to the displacement. We did that already when we used Newton's second law along the x-axis. Remember that the force breaks down into components. Each component has a different job. This one, is lifting up, so you decrease the friction, but this one is the one that moves it forward, provide the acceleration. So when we're going to find the work done on the crate by you, you're going to use only the X component, right? The component parallel to the distance. Agree? Very important to understand vector. Okay? It's not that easy to understand, but each component has a different job. So the work done by you on the box will be equals to the component of the force parallel to the displacement times your displacement or the distance. It's not really a displacement like connect first point to last point. It's really a distance. Because if you go zigzag, you have to find the whole distance. So that will be 30 times 10. So that will be, yes, 300 joules, right? So that will be how much energy you transfer to the box, right? ATP, phosphate, whatever, electron chain. I'm sure you know that better than I do. And boom, 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 creatine, boom, 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 right? Transfer energy. And that will go to increasing the kinetic energy. Okay? Okay, so try to do this one. You can help each other. Sometimes it's hard to find the X component. So what do? We look at the tail of the vector. We make a cross. Okay? And you find the component along the X. So it's a review. We need to find the component of the force along the displacement. It's not the displacement, really. In that case, it's a distance, right? So but he's going along a straight line, so it makes things much easier. So how we have a push here. So don't forget everything you have learned before. So you have a force. A force is a vector. How do we find component? Just review. You make a cross. Make a cross here at the tail. This is the tail and this is the head. And you see, if this is 60 degrees, that's going to be 60 degrees. So you have the angle with the positive x-axis. If you have the angle with a positive x-axis, taking the cosine will give you the x component. You want the component here along the x. Okay, I don't know, maybe I should have this color here. This is your vector here. This is a vector. And this is your 60 degrees. So the vector has two components. Same thing over and over again, but I know it's hard to digest. You have the x component of the vector and you have the y component. The y component is pushing into the ground, which you want, right? When you have a lawn mower, right? You want to go to push in the ground to cut the grass very, very short. And this component is the one that helps move forward, increasing the energy. So the work done by you on the lawn, whatever, lawn mower, I don't know if I say it right, lawn mower. Okay, it's gonna be the force, which is what? 20 Newton times cosine 60 times 150. Yes? So you have to know, if you take the MCAT by heart, cosine 60 means you divide by 2. So 10 times 150, which is 1500 joule. If there is no friction, that will be equals to the work, that will be equals to the change in kinetic energy. Of course, you're going to have friction. So if you are moving at a constant speed, that means you have kinetic friction here that's stealing the work that you have done. And if you are moving at a constant speed, that means the net work is zero because it doesn't increase the speed. Yes.
If they gave us the kinetic friction, would we have to subtract that from the work?
Yes, very good. What's your name?
Laurentina.
Valentina?
Laurentina.
Laurentina? Yes, yes. Good question. So the work done by friction is on the lawn mower, but whatever, it's going to be a negative. The kinetic friction times 150. So you have to subtract to have the net work. If they are equal to each other, meaning it's moving at a constant speed, so then the net work will be equals to zero. So you're right. So the net work will be the work done by you plus the work done by friction. If the speed is constant, so of course the net work will be equals to zero because there is no change in kinetic energy. Is that clear? So it means you make, I don't know, 2,000 a month, but you withdraw 2,000 a month, so there is nothing left. So in that case, you cannot be in negative. It's always zero or positive, not like bank account. So kinetic friction, remember, is the coefficient, so it depends on the grass, the materials in contact, times the normal force. And let's review. Up equals down. Up, you have the normal force, and down, you're going to have the weight plus the y component of the force, right? So that's from the last unit. Agree? It's just reviewing. So if I do a free body diagram, you have, what do you have? You have the y component of the force, you have the weight, of the, that's the, what it's called, the lawn mower. I cannot pronunciate, and that you have the normal force. Okay, just to review. So along the y-axis, it's in equilibrium. Normal force is up, weight is down, the y component of the push is down. You are pushing into the ground. Any question? More you push, more normal force you get. You always imagine that the ground is made of little spring. Okay, you compress more, you're gonna have more restoring force. Any question? Okay, and I do recommend that if you are taking the EPCAT, why not? You have to do the problem from your prep book. Or you have free problems. If you go to their website, or it's very cheap, you can practice. So you open the unit that I'm doing. So that way you save all the problems somewhere. I have also a YouTube playlist. So anyway, what about this one? Try to do it. So you can help each other. So it will be easier. That's going to be for the final, right? We are reviewing for the final work done on a system. So she's transferring energy here. So the force is 45 Newton. Okay, you can make a cross here at the tail. So that's going to be 50 degrees. So it has two components, the X component here, and then you have the Y component. Aye, aye, aye. So the work done by her on the suitcase is going to be what? What is it is doing the work? Is it the all 45 Newton or only the X component? It's going to be the uh, X component. Thank you. What's your name again? Huh? Peyton? Okay. 45, cosine 50, and times 75. Yes? So you do it like we're reviewing for the final. What do you complain about? Stay with me. Don't space out. Focus. Joules. Agree? Okay, it's easy. It's a force times distance that will be a work, and the force is always parallel. It's a parallel component, it's a parallel component, it's a parallel component. Because a vector comes into component, each component has a different job. So you need to find a component. Okay, benching. I heard that the mayor of Miami, he can bench like did you see that video? 235 pounds, like crazy. Do you see the video? 225 pounds. Do you see that? You see that? How much is it? 225 pounds. And the mayor of New York City? No comment. Okay, 225 pounds. It's a lot. 225 pounds is really a lot. So anyway, no comment. So the work done. So here he's doing work against gravity. So you see that the force that he's applying, okay, is in the same direction as the displacement. So the work will be positive. But at the same time, gravity is doing negative work. Okay, because so this force is trying to increase the kinetic energy, and gravity is trying to slow it down. So if he moves at a constant speed, what's going to be the net work? If there is no change in speed, the net work will be 0. Very good, right? Because you are doing work against gravity. If the speed does not change, the net work is 0. Now you go down, but usually you have to do it at a constant speed, because if it goes too fast, the outcome might not be very good. But if you go down, the work will be negative because you try to slow it down. But the work done by gravity is positive because it's trying to accelerate, right? Okay, so it's just a definition that gravity is said to be a conservative force, right? Why? Because if you go from here to there, or if you go from here, you take a walk to the far side and you come back to the same final position, the change in potential energy will be the same. The change in potential energy depends only on the initial position and the final position. Or you can say that the work done by gravity will be mg delta h. Okay, so gravity is a conservative force because it doesn't matter which way it goes. At the end, it's just this delta H. So whether you go from here to there or if you go from here to there, it will be the same change in potential energy. It will be the same work done by gravity. So each time you have a force connected to potential energy, what matters is the initial position and the final position. In between, we don't care. So if I go from here, typical question on MCAT, for example, I go from here, I go boom, 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 I go to the library, I come back to the same place. What's going to be the change in potential energy? 0. What will be the work done by gravity? 0. Typical conceptual question. Okay, because you go back to the same place. Your potential energy has not changed. So each time you have potential energy, like you have in chemistry, between the bonds with hydrogen bond, what matters is the configuration, or the initial configuration and the final configuration. In between, we don't care. Okay, so you see here, conservative force, gravity is a conservative force. You go here, you go back to the same place. The change in potential energy is 0. The work done by gravity is 0. Okay, now, friction is a non-conservative force because it does matter what's going on between initial and final. So if you go, what I mean by that, if I put my bag here to there, I'm going to lose energy to friction. And if it fails, I go here, and I go there, and I go here, and I go there, and I go here, and I go there, I'm going to lose even more to friction, more heat. So the path matters. So the work done by friction will be equals to the force of friction times the path. So if you go to zigzag, you have to take the zigzag path. You have to include that into your equation. But if you find the work done by gravity, it doesn't matter. So it's the final position minus the initial position. Agree? So if I want to find what is the work done by gravity in that case? 0, very good. But the work done by friction is not 0 because it keeps rubbing and rubbing and rubbing. So you keep losing heat, you keep losing heat, you keep losing heat, you keep losing heat, you keep losing heat. So at the end, the work done by friction will be equals to the force of friction times this path. Exactly, all this distance. So friction is said to be non-conservative. It's lost. Bye bye. You don't get it back. Okay, so that takes us to the work kinetic energy theorem. Yes. Here.
No, the equation for friction.
Okay, so the work done by friction is always negative because it's stealing energy, it's trying to slow down the system, and that will be the kinetic friction, which is parallel to the displacement times the distance. I should not say displacement because displacement you think a straight line. No, it's not a straight line. You have to go through the path. Okay? Okay, so the net work equals the change in kinetic energy. So that will be called the work kinetic energy theorem. Okay, so try to do this one. Yes, so you push, it's the same story, right? You are pushing a box here, doom, doom, boom, boom, pam, pam, pushing a force here, 100 Newton. So you are transferring energy to the box, but kinetic friction, which is always parallel to the path here, is to the left, is taking away energy. So it's stealing energy from the box. So the work done by you on the box, it's going to be, the distance is 5 meters, so it's going to be 100 times 5, which is 500 joules. Do you agree? Right? The work done by friction on the box, it's going to be negative 50 times 5, which is negative 250 joules. Agree?
Yes.
And you balance out the account, right? Whatever comes in minus what comes out, that will be the network, which is 250 joules. So it has a net increase in kinetic energy because the work goes to kinetic energy. So it's going to move faster. Okay, so we're going to say that the net work equals to the change in kinetic energy, which is 250 joules. And then it says initial velocity is 0, final velocity idk, okay, I don't know. So I'm going to use this to find the final velocity. So what's the equation? The net work done on a system equals the change in kinetic energy. And the change in kinetic energy is 1/2 mv final square minus v initial square. So we have 250 equals 0.5. The mass, which is 50, bless you. Final idk minus initial is start from rest. So you have to do it in your head. If you are taking the MCAT, you have to force to take it in your head. You can do it in your head because you see this is 25 and here you have 250. So 250 divided by 25, it's going to be 10. And then you don't need a calculator because you know that 3 times 3 is 9. So it should be 3 point something. And you look at the multiple choices. So the final should be about 3.2 meter per second. So you have to learn to do things in your head. Agree? Okay. You can go to physics. Oh, I just wrote a recommendation letter. If you need recommendation letter and you think you have good grades, ask me before that's thing. It's gonna be my last year. So if you do it next year, it will be too late. I mean, next school year. So physical therapy is really good. 248. So anyway, so 100 Newton is needed to slide the box across the room, and the box moves on. How much work must be done? And that's easy, right? So the work done will be, it's going to be what? It's easy now.
300.
Yes, very good. At 300 joule, right? But if now you have friction and the friction match your apply force, that's going to be minus 300 joule, right? So what's going to be the net work? 0. Okay, so there is no change in speed. Right, so that means that, and we knew that because the net force is 100 minus 100 equals 0. So if the net force equals 0, that means acceleration equals 0. That means the speed is constant. Okay, so if the net force is 0, it can move at a constant speed or constant velocity, or it's at rest. So in that case, it would be moving at a constant velocity. There is no acceleration. Any question? Okay, let's do things easy. So we review for let's review for the final. Okay, all that will be for the final. So that's it. You are done with the hard stuff. Okay. From now on, it's gonna be easy. So that's the mass. So kinetic energy of the boat. Okay. And they have the same kinetic energy. So kinetic energy is 1/2 mv squared. So now it's a problem about kinetic energy. So kinetic energy of the boat is 0.5, the mass, and the speed squared. Kinetic energy of the jet ski is going to be 0.5, the mass, and we don't know. But we know that they have the same kinetic energy. Okay, so it's just a simple algebra problem. You can cross out the 0.5, you cross out the 100, you see, 36. I'm going to do it so make sure everyone is on the same page. So again, you have to practice doing in your head, 0 goes bye-bye, 0 goes bye-bye, 0.5 goes bye-bye, 0.5 goes bye-bye. So V squared equals 36 times 2.4 square, and you do it on purpose so you can do it in your head. Okay, because then you take the square root. Okay, square root of 36 times 2.4 square. Square root of 36 is going to be 6. Square root of 2.4 square is going to be 2.4. So you see in your head it's going to be 12 or something like this, or 13. So practice mental math. Okay? That's not too hard. Okay, so this one, they like also to mix the units. So you see, you want to find the kinetic energy, which is 0.5, the mass times the speed squared. But they don't give you the speed, but they say it traveled a distance of 5 in 4 seconds. So you remember the definition of speed? Just distance over time, right? Meter per second. You look at the unit and you know the equation, right? So 1 and 1/4, which is 1.25. Okay, so you can do the computation. So kinetic energy will be 0.5 times 7 times 1.25 square. I don't know if you can do it in your head. I can't. But if you can, good. Okay, make sure you know how to do it. Okay, any question? Okay, so that's easy problem. Okay, try to do number 3. Okay, I give you some time. You can help each other. How much work? Okay, so they just want you to remember the definition. Work, by definition, the work-kinetic theorem. Work is the change in kinetic energy. Okay, so the network, so that will be the network equals the change in kinetic energy. So if you want the kinetic energy to increase, so if you want the speed to increase, you need to apply a force over a distance. That's how energy can be transferred. So you need a thrust. And it's net because then you have to include the kinetic friction, right? So do it so we review at the same time. So the network equals the change in kinetic energy will be final square minus initial square. So mass. So final, you need your calculator. Yes, you're right. What's your name again? William, yeah. William. 398 joule. Yes? Okay. Okay. And then number 4. Okay, so this one is super easy, but just to make sure. Okay, from rest means initial velocity is 0. So the network, again, it's going to be 0.5, the mass, and the change, so the final velocity is 0.55 squared minus initial 0 squared. It's going to be a big number.
1,032,948.
Okay, so 48, right? So is it 1,000? So 1,32948 joules. So 1, 2, 3, 4, 5. 1.33 times 10 to the 5 joule. Scientific notation. Okay? So next is you can use potential energy, or you can use okay, so the work done by gravity is also equals to the change in potential energy. So anyway, so you have a mass here, and gravity is going to apply a force, gravity here. So it's going to move for a distance here 33.4 meters. So gravity is doing positive work because you know that because it's trying to make it go faster. If something is trying to make a system faster, going faster, positive work. If it's trying to slow it down, negative work. So the work done by gravity, which is so that will be gravity on what? On the boulder will be the force. The force is the weight times the distance is 33.4. Okay, so it will be 7.64 times 10 times 33.4, 2552 joules. Agree? Now you see that will be equals to the potential energy. So you see what's happening here is that you start with potential energy and you end up with a change in kinetic energy. So this is called conservation of energy. You start with potential and you go to kinetic. So that's what we're going to do next. Conservation of energy. You go from potential to kinetic. The change in potential energy, you have lost potential energy and it turns into the kinetic energy. Okay, so this is from your book. I'm not going to solve it because it's heavy in algebra, but I just gonna lay out the equation. It's from Cotnell and Johnson, right? What is its final speed? So that it means that the work done by the thrust on the craft, the spacecraft, will be equals to the work done, which is the force, so 0.056 times the distance, so 2.42 times 10 to the 9. That will be equals to the change in kinetic energy, so 0.5 times the mass times the final speed minus initial speed square. Okay, so I'm using work kinetic energy theorem, the work done equals the change in kinetic energy, except that physics is done and then algebra takes over. So you just have to solve for the final speed, and you can do that on your own. Okay? So that comes from Cotnell and Johnson, and if you do the math, you should find 805. Okay, 35. Should we do all that? Okay, let's do just number 4. Let's do number 4. It's a wagon. Do you see the wagon here? So 100 Newton. This is 60 degrees, right? So it has two components. It has a x component here, and it has a y component. And the distance here is 10 meters. So the work done by the lady on the cart will be equals to the x component of the force, right? So 100 cosine 60 times 10. Cosine is 1/2, so 50 times 10, which is 500 joules. Agree? Okay. So the work done by friction on the cart, it's gonna be negative because it takes away times 10, so it's gonna be minus 400 joules. So then the net work done on the cart will be equals to 100 joule, which equals to the change in kinetic energy. Okay? Okay, one more. So all those problems, you find them in Dropbox. You know, I go over them. The tree. We're gonna do the tree. So try to do it on your own. Okay, so it's a review. Do you have a test or something today? No, there's no test because the class is empty. I don't know why. Maybe because there was no pop quiz. Right? I should give extra credit for those who. Huh? I think I think so. Maybe at the end you write down your name. If you stay till the end, you can write your name. I don't know what's happening. It's like I'm leaking the class. Okay. Uh, so you have the tree. So you have a speed here. That's before, right? So you have 2000 kilogram. And after the car goes into the tree. So So all that kinetic energy, is going to turn into going into the tree. So doing a force, applying a force over a distance. So now it's stop. And so it's going into the tree here by 50 centimeter and it stopped. So not only if you apply a force over a distance do you change the kinetic energy, but if there is a change in kinetic energy, then you can apply a force over a distance. So energy is destruction. How much you can destroy by applying a force over a distance. So if you go a big distance, the force will be small. If you go a small distance, the force will be big. It's like punching. It's the same idea, right? If someone boxes and roll over, the distance will be small, the distance will be big, so the force will be small. So if the distance is small, the force is big. Okay, so all that change in kinetic energy will go in applying a force over a distance. If the distance is small, that force of impact will be very big. So to find the change in kinetic energy, that's going to be 0.5, 2000. The final speed is 0. Initial speed is 12 square. So that's going to be negative. Did you get that? 1, 2, 3 joule. Yes? You can do it in your head because 12 square is 144. So that you have to know. And then half of 2000 is 1000. So 144 times 1000, that will be negative A. So B, the work done by the car on the tree, by definition, is the change in kinetic energy. If there is a change in kinetic energy, there will be done work. So that work done will be 144,000 joule. So all that kinetic energy turns into applying a force over a distance. If the distance is small, the impact is huge. So that's why if you have an accident with a car, right, if you go into something by a small amount, the force of impact is going to be destroying. It's going to be really bad because there is a trade-off between distance and force, right? Okay, C. Talking about force, all that work done on the tree, okay, the car on the tree will be turned into force times distance. So that will be the force on the car, of the car on the tree. So force times the distance is 0.50. So the force, you take this and you divide by, you multiply by, you divide by 0.5. Are you with me? Okay, you do negative 144,000 equals the force times 0.5. So you divide by 0.5. So it's going to be negative 288,000 Newton. Okay? Okay. Any question? So sometimes, when they are doing work here, they are always doing work, and you see they have poles, like poles that they want to put inside the ground. So they take a weight here, okay, and they drop it. So all that, the work done by gravity, okay, is going to go into kinetic energy. So now it has kinetic energy, and all that kinetic energy is going to go into applying a force times a distance. And because the distance is very small, the force will be huge. Same thing with a hammer. Let's say you have a hammer. I don't know how to make hammer. It's like a hammer here, and you have a nail. Oh, this is so bad. This is a hammer. Okay, and I want to put a nail in wood, in some wood here, and I have no muscle. There is nothing here. Okay, so but if I do it over a very large distance, I'm gonna swing over a large distance, right? So I'm gonna have a large kinetic energy. That kinetic energy is gonna turn into force times distance going into here. The distance is small, so the force will be big. So we are transferring energy. So it's a trade-off between force and distance. Okay, and then there is a Hooke's law that you remember. Hooke's law. So if you have a spring or resistance band, right, as you increase the stretch, the resistance is going to increase. Agree? That's the idea of those Pilates class, right? You're going to pull and you're going to feel a stronger restoring force. So the force here is proportional to the displacement. So the force, Hooke's law is called negative K delta X. So as you increase the stretch, the restoring force is going to increase. K here is called the spring constant. I forgot if we did that already or not. Let's see. It's called Hooke's law. It's named after James Hooke. He was the enemy of Newton. They really didn't like each other. Okay, so that you have a spring. I'm going to apply a force. That will be displacement here. And I'm going to put everything there. I'm going to apply a force. And what do you see? Do you see the restoring force? I'm applying 45 Newton. So you have a restoring force of 45 Newton, 40 Newton. So more stretch, more restoring force. And they are proportional to each other. Okay, so if the stretch is that much, this is 25 centimeter, the restoring force is 50 Newton. If I have more stretch, which is 50 centimeter, the restoring force is 100 Newton. So it's proportional to each other. Agree? So my point is that when I'm doing this, I'm storing energy into the band. I'm storing energy into the spring. Let's say it's a spring or resistance band, right? So it's called potential energy. Potential energy can be restored. I can turn that into kinetic energy. So I'm doing work, right? I'm applying a force over a distance. I'm storing energy into potential energy, and that can go back to kinetic energy. So I'm not going to do the math, but I'm going to tell you that the work that you are doing, the work done by you on the spring will be equals to 0.5 times K times the change in length. So if you are stretching it, okay, that will be your delta X, or you can compress it as well. That will be the change in elastic potential energy. Okay, so again, each time you have a resistance band or a spring, You can stretch it, right? You are storing energy. That energy that you are storing, the equation is easy, it's 1/2 K. K is a spring constant times the amount by which it's being stretched. K depends on the stiffness. So if you buy those resistance bands, you go to the gym, they always like this, right? So you have heavy, you have easy, you have very easy. So all that depends on that constant here. So if you have a one which is very hard, that means the spring constant will be large. If you have a green one, usually they are the easy one, this one is a medium one, then K will be small. So K is a constant that depends on the stiffness to make it easy. Stiffness of the spring. Okay? All that that take us to number number 7. Okay, let's do something easy. So now it's compressed, but the equation is the same. So you have a spring here, it's happy, minding its own business, not asking anything to anyone. Okay. And then you come and you make it very unhappy because you're going to compress it and it doesn't like to be compressed. It gets very, very upset. Now you compress it by a distance of 30 centimeters. So it's being compressed. So it's going to complain. Okay, it's going to resist. It's going to push back, right? You have a restoring force here. It wants to push back. And here, this is you, and you're compressing. And this is the issue that you apply. So you are pushing here. You are in blue. You should put in blue. You apply your force, and then you have this restoring force. Now the amount of energy, the amount of potential energy stored in the spring will be equals to 0.5 K, and the amount by which the length was changed. So the change in potential energy will be 0.5 times 150 times 0.3, and there is a square here, square. So 1/2 kx squared, that's the equation for elastic potential energy. Okay, it's called elastic potential energy. Did you get? Which is what? Yeah. Joules. Okay. So I don't know if you remember the beginning when I talked about energy. Let's see. You have different kind of potential energy. You have gravitational potential energy, because you can imagine that gravity is like a spring that you stretch, right? So the mass will go back to a lower level of energy. So this is called gravitational potential energy. On Earth, it's easy, mgh. And then you have chemical potential energy. That will be in the electrons, in the bonds, right? Between atoms, right? So if you are releasing ATP, you see those electrons, they go from a higher level of energy to a lower level of energy. So at the end, in biology, everything Everything is physics, right? It's just electron moving from a higher level of energy to a lower level of energy. You are releasing this energy, okay? And then you have nuclear potential energy inside the nucleus, right? So you break a nucleus, you release that energy because you are losing mass, mc squared, and you have elastic potential energy in a spring that you stretch or compress, and that will be equals to 1/2 k delta x, the change in length, square. And k is a spring constant. It depends how stiff is the spring. Okay? So this energy has a restoring force that wants to lower the system, lower the level of energy. Okay, so that takes us to conservation of energy, right? We've seen conservation of momentum. Now we're going to see conservation of energy. If there is no friction, the mechanical energy will be equals to potential energy plus kinetic energy. And you can swing back and forth between them. Okay, so just quickly here, for example, here at the end, it has no potential energy because this is level 0. It has 100 joule kinetic energy. How much potential energy it has to begin with? 100, right? So imagine you have euro and dollars, and you are changing without anything taking money in between. So the total amount of energy will stay the same, except you can have everything in potential, which is 100 joule, everything in kinetic, which is 100 joule, or if you have 75 potential, how much kinetic do you have? 25, right? And then 75 kinetic, here you're going to have 25. Okay, so the way you can remember it, you can see that if there is no friction, if there is no air resistance, energy is inside a reservoir. The level here will not change. It's 100 joule. But you start with only potential. So everything is in potential. Potential is in green. And then little by little, right, you still have the same reservoir. You still have 100 joule. But some of it will be potential. And now that potential, some of it already turned into kinetic. But the total amount is still 100. So you have 25 here and you have 75 there. So then you still have the same reservoir, still 100 joule, but now you're going to have more kinetic. So potential here will be only 25 joule. And then here you're going to have 75 joule. Okay, and at the end you still have the same reservoir. Total is 100, but everything will be in kinetic. Okay, so the total amount stays the same. So it's like you have $100, and then you have, I don't know if $1 is €1, so 25 euro, $75, 75 euro, $25, and 100 euro. Except that it doesn't happen this way because the bank is always taking something from you. So the level is always decreasing. That will be friction. Friction is taking away. Okay? So you can swing back and forth. So for example, I don't know what happened to me this day. That was a long time ago. I think it was 15 years ago, something like this. So you start with 15,000 joule. 11 to 50, how much kinetic energy? Yeah, so it has to add up to 15. Okay, so it will be 3750, right? And then you have 7500, 7500, and then 11 to 50, and then everything is in kinetic energy. Okay? So we'll do that next time. Conservation of energy. Okay, so I've found this super cool video. So that goes from potential, kinetic. Trampoline is elastic. So potential, kinetic, elastic, kinetic, potential. Of course, you're gonna lose to air resistance, but if you don't do it too long, not too much, right? So potential, kinetic, elastic, kinetic, potential. Okay, potential, kinetic, elastic, kinetic potential. Isn't that cool? And so that's all over Marina. You see potential, kinetic, apply a force over a distance. Potential, kinetic, force times distance. So the distance is very small because they are putting pole, inside. So the distance is small, the force is big. And then you have one which is very inspiring. Very, very inspiring. Oh, this is very inspiring. Do not give up. That's the message. Okay. Potential, kinetic, elastic, kinetic, potential. Potential, kinetic, elastic, kinetic, potential. And keep going like this. This is very artistic and it's all physics, right? Oh. So the idea is do not give up. Keep trying, passing the class 2053. Eventually you will pass, right? Elastic potential, elastic kinetic potential, elastic potential, elastic kinetic potential, and here. Okay. So if you want extra credit, but maybe you don't want extra credit because that's going to give me